One-dimensional arrays are organized linearly, as we saw in other videos. They're contiguous to each other element-wise. So that is one-dimensional array. In this video, let's talk about two-dimensional array. In fact, there are many applications out there that require data to be stored in more than one dimensions. Many applications require that data to be stored in more than one dimension. So we see that a lot in machine learning and data sciences, where computations requires data be placed in multi-dimensions, right? So in machine learning, we can have, a data dimension that goes up to like 100, 2,300. So we see that a lot these days. But how is this manifested and done in C or C++ or Java or Python? So in the next video, we're going to talk about the two-dimensional array, not getting into three, but two. We're going to look at how two-dimensional array is formulated or represented in C or even C++. We will look at how these two-dimensional arrays are declared and how we pass them into other functions. Instead of representing data in one linear fashion, a two-dimensional array has columns and rows, right? Just like this. So in fact, in C and many other languages, in C++, right? A two-dimensional array is an array of one-dimensional array. So if you take this as one-dimensional array, then you can see the array goes like this, right? So that's the first row, right? The second row is the same as that. So that we have basically an array of one-dimensional array going from left to right. Or you can represent, right, this entire table, column-wise, right? So now you can have array going from, right, the vertical arrays, right, going from top to bottom, right? So as you can see, every single column in this case will be represented by a vertical, right, array. So it doesn't matter how you represent it, but it's this whole idea of having this two-dimensional array simply just means, having an array of arrays. This is a pictorial representation of a two-dimensional array. So we call it table here. If you look at, this table formations here, array indexing, right? Or element. A two-dimensional array has this syntax here. The first one is what we call row, right? Number. The second one is our column number. So as you can see here, if you start up from the very top, top left corner of the table, indexing starts as right 0, 0, right? So 0 means indexing for the row is 0, and column indexing is 0 as well. So when you move down the row, so this is row number 1, number 2, number 3, number 4, right? Array indexing starts 0. As you can see here, this number, right, the very first number, which is the row number right here, increases, right, according to the row number that you have here. Column number is the second indications here. So this is column number, right, 1, number 2, number 3. Again, array indexing starts with 0. So this is how we label this. As you can see here, as we move right from left to right, the column number starting with 0 goes up, right, 1 at a time, 2, and then 3, so on and so forth. In the very bottom right corner of the table, its indexes would have been 4, 3. So hopefully this illustrates, how array indexing, works in a two-dimensional array. In this case, this should be table. This example illustrates a couple things. First of all, this is a function called filled array. Namely, its purpose is to take a two-dimensional array, which is represented by table, right? This is the name of the 2D array. And we will iterate through, right, the number of rows and number of columns, right, in this function to fill in the data, right, in every single rows and columns in this two-dimensional table. Second thing is the number of columns represented by this constant, right? So I don't know where this is defined, but you have to assume that this max column is defined is some sort of constant. This could be a pound, right, defined constant, or it's simply just a declared constant globally that's outside of this function. So there's a number associated with it. We pass, in addition, a 2D table. We also pass in by value, right, the number of rows that we have. So because this is a two-dimensional table, right? A table is a two-dimensional with columns and rows. We have to have a nested for loops, okay? There's an outer loop, there is a inner loop. So in this case, we decided to use number of rows as our outer and the number of columns as the inner. In fact, you can actually switch the number of rows and columns, right? Meaning you can have column here and row here. It doesn't matter as long as you're going through, right? All of the right elements. So that's what we're doing here. You can also have this nested loop that goes, from, left, right to right. And then for each of the elements here, you start going down. Okay, so the looping structure that we have here is actually this, okay, not this one. So that's what we're doing. And then we fill in the table with, these specific elements, values. We don't have to concern with these values, but just note that, this is how we are filling our data into two-dimensional table. And notice the start, right? The starting location, the starting value of your column. So are we missing column number 1, which is index 0? So remember, this is column 1, right? 1 all the way through, right? Size or column size, right? Column size minus 1, right? Because this is a less than max column. So if this max column is 5, then this column only goes through, 1 all the way to 4, right? What about 0? There's no 0 in this loop, right? Well, the reason is because the 0 column has already been initialized, right, with this, so that we don't have to worry about that. This is a memory view of what user sees, right? So this is our two-dimensional table. Like I said, this is row, right? And this is direction is what we call column, right? Okay, and these numbers represent indices. Okay, they are not the value of the table. This is just a memory view. So 0 means 0 row. This 0 means 0's column, right? So 0 row, column number 1, 0 row, column number 2, and this would be 0 row number 1 and column number 1. Okay, so on and so forth. That's what we see, right? When we formulate our code and start dumping data into it, we use indices, that kind of are, represented in this fashion. In reality, inside the memory, like I said, a 2D, right, array is what? Is an array of 1D arrays. Okay, so you have in this fashion, right? Each row is an array. So this is row number 1, right? 0. Row number 2 is another array, right? So there's actually arrays here, right? 2, like this. So when you're, let's say if you take a bird eye view of the memory, right, that you see in, let's say this is your memory cloud. These rows would have been represented, right, as this block right here, for example. Okay, this will be row 0, right? And you have row 1 maybe sitting right here, right? And row 2, maybe sitting right here. Okay. And the reason is we don't know, where the memory is allocated inside. Let's say this is your stack memory, right? We're not talking about dynamic memory, but dynamic memory is similar to this, right? There's no telling as to where this entire block of memory is allocated for each row, but it is guaranteed that every single element inside the row, they are sitting next to each other, okay? Meaning they're consecutively, they're sitting right next to each other. If this memory space is 1, the next one is 2, the next one is 3, and so on and so forth. That is assuming that memories, goes up in number, but sometimes memory goes down too in terms of their hexadecimal designations. So that's outside of the scope of this discussion. The point I'm trying to make here is what you see inside the memory is a whole block of rows or arrays that form this entire table to begin with. So this is the table. Sometimes they could be sitting all next to each other, meaning row 1 will be sitting to next, right? Row 1 will be sitting next to row 2, and then row 2 will be sitting next to row 3, so on and so forth. But that's not guaranteed. So that is what I'm trying to to convey in this memory chart with respect to declaring and initializing a 2D array. This is an example of how we convert a two-dimensional array, right, into a one-dimensional array. So the effect of doing so, you have rows, you have columns here, right? And the thing is that we will transition this, right? We'll convert this into a one-dimensional array. So there's only one row, right? And many, many columns. So that's what we're trying to do, right? So a lot of times in some textbooks, industry, they call it flatten, right? How do you flatten a multi-dimensional array, in this case, two-dimensional array, into a one-dimensional array? So 2D, 1D. So we're not going to get into the mathematical formulation of it, but just note the technique for doing so. So the way that we do it is we come up with a nested for loops. And this involves going through every single row, every single column. And the formula involves multiplying rows, the column, right? The columns that you have. And this is very typical, right? And if you do the math, you can also convert, for example, a two-dimensional array like this, right, into a vertical representation, like going from top to bottom, like 0. This is number of row, right? Row size minus 1, right? So, or, right, as the above example illustrates, is convert them into a flattened, right? This one row, right? This is one column actually, with multiple columns, and this is one column with multiple rows. So formulation will be kind of similar, right? For this particular example right here, but this one, right, illustrates the conversion into this 1D, right, array. And then the second for loop here simply just prints all of the elements out from this 1D array. This example illustrates how we pass one-dimensional array into a function. So in this case, we're passing, we start out with a two-dimensional array. So this is a 2D table. And by the way, these are curly braces, okay, curly braces. So this is how you use initializer. This is what we call initializer. Okay, so you can use the initializer to kind of hard code, right, the content of your two-dimensional array. What we're doing here is now that we know table is 2D, we can simply, right, by saying table, right, with a row number to fetch, right? So if we said, let's say this row is 0, then essentially what we're getting is if you do table 0, you're getting this entire thing. So what is this entire thing? This entire thing is a 1D table, right? So saying table, right, 0 gets you everything here, right? So I hope this makes sense. But if you say, let's say, for example, this is 0, right? 1, 2, 3, 4. If you want to fetch this entire table right here, right? This one-dimensional table, so then what you need to do is to write table 4, right? Because this is the 4th index. So what you're getting out of this, right, is actually a 1D table, right? So what we're doing, so 1D table is essentially just an array. So this print square is a function that takes one-dimensional array, right? So this X, it's really that entire, right, row of elements, right, at the indicated row number, right? Starting with row equals 0, right, all the way to max row. So whatever this max row is, in this case, the max row is actually 4. So array index is 1, 2, 3, 4, 5. Max row is 5, right? So the very last row number is 4, right? So this gives you the idea. So you're able to print every single one of these elements out, one row at a time, right? As you can see here, once this 1D, right, this entire row goes into this print square function, we set up a for loop here to iterate every single column 0, column 1, 2, 3, 5, all the way to the max column size, whatever that column size is minus 1, right? So there's only 4. So max column is actually 4. So very last index for this one is 3, right? So we're printing this out one at a time. So we end up with, the elements. Okay, so that's how we are, kind of using a two-dimensional array, converting it into one-dimensional. There's really not a conversion, but how we access, right, one-dimensional arrays from a 2D table and try to use that methodology to print every single elements out. This is another example. So we have a table that has these various different colors. So what we want to do is, and this table is actually 6 by 6, right? So there's 6 rows and 6 columns. What we want to do is to have these colors represented by a different integer, and these are the values that we want. In other words, at this diagonal line, we want the value to have 0. Anything that is above it would have value of 1. Anything above it or below this diagonal line would have value of -1, right? So let's see how this is accomplished by writing nested for loops through this table. The first thing that we need to do is to declare, right, this table of 6 by 6. So the way we do that is similar to having a white dimension, but now we have 2 brackets, right? 2 bracket pairs. The first pair represents row numbers or the size thereof. The second part represents column size. So 6 by 6, this is how we declare. Now, declaring table on the stack means that there is memory reserve. So there's a total of, right, 6 by 6. There's a total of 36, right? 36 what? 36 integers, right? So we know that each one of these, right? Every single one of these elements inside this 6 by 6 is a integer. So each integer is actually 4 bytes, right? So there is a total of 4 times 36. So this turns out to be 144 bytes, right? So this means that compile time, right? Your program reserves 144 bytes of memory space. These are contiguous memory space, meaning they're sitting next to each other, right, in your stack, the way that this is declared in memory, not as a 2-dimensional array, but as a one contiguous, like long stretch of bytes. Okay, there's actually a total of 144 bytes here. Okay, so that aside, right? This is what's happening inside your memory. Now, let's look at the very next step. We write a for loop here. As you know, this is a 2-dimensional array, so there needs to be a nested for loops in there. So there's outer loop, right, for loop, and the inner loop. So with respect to should we start with a row or column, doesn't matter. But this code illustrates how we, get this going, starting with rows. So technically, you can have column right on top. So the thing is to write this, this nested for loop, starting with index 0, right, all the way to 5, right, because 5 less than 6. You do the same thing with column because this is a square table, right, 6 by 6, and then you have the standard initialization, the conditionals plus the increment as part of your for loop syntax. And the very first, right, if statement here, so this is all conditional, right? Is to fill in the diagonal, right? So what does diagonal mean? If you look at rows and columns, they all share the same number, meaning 0, 0, 1, 1, right? And then 2, 2. And notice that these elements, right? And 3, 3, so on and so forth. Every single one of these elements needs to have a value of 0. So basically, wherever you come across a number row and number column matches to each other, meaning they are equal, we want to set that value to 0. So with respect to these element positions, we want to have 0 associated with them, right? So the blue one is the indices, right? 0 is the value itself. So that takes care of the first one, right? The second one is, remember, everything above it needs to have a value of 1. This needs to have a value of -1 beneath it. So the way you do that is if row is greater than column, right? So if you look at this, every time when you have a row number that is greater than column, meaning they're all kind of filling, in this whole area underneath this diagonal line, right, on the bottom. So this entire, right, triangle right here would have value of -1. Similarly, if, right, column is greater than row, right, then we set everything to have a value of 1. The reason why we can do that, actually, we don't even need to have an else if, because we already know there's only 3 conditions there, right? Either, you have 0, 1, or -1. So if you take care of 0 condition, and -1 condition, the other one is the else, right? Everything else would have a value of 1. So that's how we kind of populate data into a 2-dimensional array using the patterns that we desire. And then this very last one simply just prints out everything. As you know, since we're dealing with a table, and this table is a 2D, right? We have to have 2 nested for loop. One goes into the row direction, and the other one goes into the column direction to print them out.